Everyone keeps asking, how big is 3i Atlas? As if it were just a number, but often, it's just a rough estimate of brightness, disguised as a certainty. This is because telescopes estimate size based on the brightness of an object. They measure light, not size, and if something controls its light, it can be any size it wants. NASA doesn't point a ruler into space. It observes how bright an object appears and then estimates its size based on that brightness and an assumption about reflectivity. This assumption is a weakness, because the brightness could come from a solid surface, from dust, or from a fine fog around the object that simulates a larger halo. And reflectivity isn't fixed. Ice can brighten, dust can darken. A crust can frost over like a windshield, then clear again in minutes. So when NASA analysts say the size changed, what they really mean is, the light didn't behave like a normal comet should. It started with survey data. The early frames made 3i Atlas look like a modest, ordinary nucleus with a faint coma, exactly what you'd expect. Then Webb took a deeper look in infrared, where you don't just see reflected sunlight, you see heat, the glow of a body that can't fake its temperature easily. And the heat didn't match the small comet story. The thermal signature implied a surface area that was inconsistent with the optical size estimate. Not by a tiny margin, by enough to force a question nobody wanted to say out loud. Why does it look small in visible light, but big in heat? Hubble added another crack. The brightness curve wasn't smooth, it had plateaus, then sudden dips, like 3i Atlas was choosing when to reflect and when to drink light. At first they blamed rotation. It's tumbling. That's the safe answer, because tumbling explains anything if you're desperate. But the phase angle behavior didn't match simple tumbling. The object brightened at the wrong angles, then went dull when geometry should have helped it shine. That's like a mirror that refuses to mirror when you move the flashlight, then suddenly flares when you look away. ALMA came in from the side with millimeter data, the cold language data, and it hinted at something even worse, a thin layer of particles around 3 Atlas. Not a dramatic tail, a tight, local sheath like dust or micro ice grains, hovering close, thick enough to reshape how light scatters. Here's the part most people never understand, and you need it simple. Telescopes see how much light comes back. If the surface becomes less reflective, the same object looks smaller. If it becomes more reflective, it looks larger. Size estimates in visible light are chained to the reflectivity you assume. So if 3i Atlas can change its reflectivity, it can change its reported size without changing its actual body at all. Now picture a cheap disguise. A dark coat at night makes you look like a shadow, not a person. In space, a dust-darkened surface can make a large object look like a small one, especially if it keeps the brightest patches turned away. And 3i Atlas didn't just dim. It dimmed in patterns that lined up with observation windows, like it knew when the big instruments were looking. NASA didn't publish that sentence. They wrote it as non-standard photometric behavior correlated with observation cadence. But you can translate that. It means the weirdness wasn't random, it was timed. Then came polarization data from ground observatories, the kind of measurements that tell you how light is being scattered by tiny particles. The polarization signature suggested a surface and near-field environment that didn't match a normal fluffy comet coma. It looks more like controlled scattering, like a thin layer of grains engineered by size distribution, not just whatever dust happens to leak out. If you want the simplest mental picture, imagine a sparkle skin, a moving dust frost layer that can act bright or dark depending on how it's oriented, like a cloak made of tiny mirrors and tiny soot. One mode makes 3i Atlas look like a harmless little comet, low mass, low stakes, easy to ignore. Another mode makes it flare briefly, then disappear back into the small size profile before anyone can triangulate a stable diameter. And NASA hates unstable diameters, because unstable diameters mean you don't know what you're actually tracking. So JPL started comparing datasets like a court case. Visible brightness says one size, infrared heat says another, millimeter emissions say there's extra material you can't see in the same way. And the only way to reconcile all three is to admit 3i Atlas isn't presenting one consistent face to our instruments. It's presenting an optical mask, not a Hollywood invisibility field, a practical mask, reflectivity control through dust, frost, microcrystals, and geometry. The creepiest clue was the repeatability. Each time the observation campaign intensified, the visible size estimate drifted toward normal comet, while the thermal estimate stayed stubborn, like it was trying to be boring in the wavelength humans obsess over, while still leaking the truth in the wavelengths fewer people read. So NASA's internal notes began using a phrase that sounds harmless but is loaded. Apparent cross-section management? Not it's lying. Not it's hiding. Just a sterile way to say its apparent size is being manipulated by its own optical behavior. And once you accept that, the next question hits you hard. If it can fake its size, what else can it fake? Trajectory, activity, composition, the entire story we tell ourselves about what it is. You know what NASA hates more than bad news? Bad measurements. So they didn't argue on Twitter, they built a trap designed to force one honest answer. They planned a coordinated watch where 3-eye Atlas wouldn't get to choose one telescope at a time. Hubble, Webb, and ground arrays would overlap like a net. The logic was brutal and simple. If it's just tumbling, the brightness changes should be smooth, shared across wavelengths, and tied to a steady rotation. But if it's a mask, you'll see breaks, fast shifts, color and polarization jumps that don't behave like a rock slowly turning in sunlight. They picked a geometry window where phase angle barely drifted, so the angle excuse wouldn't save it. Same lighting rules, same distance, long stare. Hubble ran tight cadence in 2 visible filters, back to back, watching color like a heartbeat. One filter for clean reflected light, one to catch haze. Webb watched in near IR, where you can separate shine from warmth better, because reflected sunlight and thermal glow don't scale the same way. Ground observatories added polarization, the quiet lie detector. Tiny grains scatter light in a different signature than a bare icy surface. The trap wasn't just look longer, it was look smarter. Force 3. Eye Atlas to show one consistent story across instruments at the same time. The first hour was boring, and that's always when you think you're wrong. 3-eye Atlas looked like a modest comet, dim, soft coma, normal enough. Then the timing got weird. Right as Webb's sequence shifted into a deeper sampling block, Hubble saw a sudden dip that was too sharp for a rotation peak sliding past. Not a gradual roll-off, a step, a clean change over minutes like someone pulled a veil across the face. Color shifted with it. The object got optically flatter, less reflective in a way that made the visible base size estimate shrink. But Webb's thermal didn't shrink. The heat signature stayed stubborn, like the true surface area didn't change at all. That's the first fingerprint. Tumbling can change brightness, but it can't decouple visible size from thermal area on a dime without a trick. Polarization jumped too, and this is the part that makes scientists go silent. The scattering signature moved toward fine grains, not solid ice. It looked like a thin layer of microparticles suddenly dominated the reflection, the kind of layer that can darken or brighten you by angle alone. NASA tried to rescue the normal explanation anyway, because that's what you do first. They fit a tumbling model to the visible curve. To make the step that sharp, the model needed an absurd rotation rate, or a shape so extreme it would tear itself apart under spin. And even if you accept that nonsense, it still couldn't explain why the thermal stayed steady while the visible size collapsed. So JPL reframed it as a surface event, not a rotation event. A fast change in the top layer, like frost blooming or dust settling. Here's the uncomfortable detail. The switch happened near the same cadence markers the team used for their observation blocks. Not exactly on the minute, but close enough to make people stop saying random and start saying responsive. NASA didn't publish, it reacted to us, because that's not how professionals write. They wrote correlated with cadence boundaries. Then they did the meanest thing they could do to a mask. They repeated the block but swapped the order. If 3-eye Atlas is just tumbling, it doesn't care which filter comes first. If it's managing reflection, the order might matter. On the next block, Hubble led with the other filter. Webb shifted its sampling pattern, and the ground teams held polarization steady. 3-eye Atlas still switched, but the switch moved. The dip landed closer to the new boundary like it was tracking the campaign structure. That is the second fingerprint. Tumbling doesn't chase your schedule. Surface physics doesn't know your block order unless something is phase locked. Now the team started comparing it to the other weird rhythm they'd already seen in separate datasets. A repeating internal cycle, a timing beat that kept coming back, whether you looked at heat, chemistry, or radio path changes. In this trap session, the reflection mask seemed to ride that same beat like the optical layer is one more output channel of the same driver. Think of it like this. If the object has a cycle, it can refresh its skin on the cycle, laying down frost or lifting dust at repeat times. That would let it appear ordinary in visible light most of the time, then briefly flare or dim in ways that scramble size estimates. And size estimates are fragile. Most quick headlines translate brightness into diameter using one guessed reflectivity number. Change the reflectivity and you change the diameter the public thinks is confirmed without moving a single atom of rock. So when you hear NASA confirms the size, understand what that really means. They confirm an apparent size under assumed reflectivity. After the trap, NASA stopped using a single visible diameter in internal briefs. They started using ranges tied to measured scattering states. That's a quiet admission that the object's reflection is being managed by a layer, not by a fixed surface. The most unsettling note in the debrief wasn't a big scary sentence, it was a small one. Photometric cross-section is state-dependent. Translation, it can look like different sizes depending on which state it's in, and the state can switch quickly. Now ask yourself why that matters. If you can't trust apparent size, you can't trust mass guesses. And if you can't trust mass guesses, you can't trust how strongly it can push its own environment. That doesn't mean impact, it means modeling. It means how you predict outgassing thrust, how you predict trajectory drift, how you plan observation risk. And it means one more thing nobody likes to say. If 3i Atlas wants to look like a normal comet, it knows exactly which knob to turn. You know what NASA does when light becomes untrustworthy? They try to corner the object with a measurement that doesn't care about shine, or at least cares less. Because visible brightness is a liar's playground, but heat, geometry, and timing can trap you if you can't change all of them at once. So the next move was obvious in a quiet, technical way. They tried to estimate a true area from thermal emission, then cross-check it with constraints that don't depend on albedo. Webb gave them the strongest anchor. In infrared, if you know distance and temperature, you can estimate emitting area more honestly than with reflected light. It's still a model, but it's a harder model to game, because you can't fake being cold if you're radiating heat, and you can't radiate from zero area. So they treated the thermal area as the baseline body, then asked a simple question. If the body is that big, why does the visible edge look so clean and so small, like a classic compact nucleus in a neat coma? That clean edge is the key. A normal comet has a fuzzy transition, dust gradient, light scattering that softens the boundary. But 3i Atlas kept producing a surprisingly crisp apparent limb in some sessions, the kind of outline that tempts you to trust the diameter. NASA suspected the outline itself might be part of the mask. Not the object's true edge, but a manufactured edge created by a tight, controlled halo of particles that scatters light in a way that mimics a hard boundary. If you've ever seen a stage trick, you know the move. Put smoke in the right place and the spotlight edge looks like a wall. So they went hunting for the halo. ALMA can see dust and gas in a way that optical telescopes can't, especially cold grains and molecular emissions that reveal density close to the nucleus. They scheduled short, repeated ALMA snapshots across the cycle, trying to see whether the near-field particle density spikes right before the visible limb sharpens. And it did. Not like a dramatic tail eruption, like a subtle thickening close to the body, a compact sheath that appears and relaxes on a rhythm. The sheath was tight enough that it could act like a controlled scattering screen, shaping the apparent boundary in visible images. That would let 3i Atlas present a clean nucleus edge even if the true physical shape is larger, flatter, or stranger than the outline suggests. Now the team tried a second trap. Watch the object against background stars during a slow drift, looking for tiny light-blocking effects. Not a full occultation, not a big event, just micro changes in star brightness as the near-field material passes in front. If the true body is larger than the visible nucleus suggests, you'd expect star dimming to disagree with the optical edge. And if the sheath is doing the masking, you'd expect star dimming to track the sheath, not the supposed nucleus limb. The first attempt was messy, because space isn't polite and background stars aren't perfect test patterns. But the trend was there. Star dimming events didn't line up with the clean optical limb. They were offset, like the edge in visible light wasn't the true edge. This is where NASA gets careful, because a trend isn't proof, and you don't want to accuse your own data of being tricked. So they repeated it. Different star field, different cadence, different geometry. And again, the dimming followed the sheath behavior more than it followed the neat nucleus outline. That's the third fingerprint. If the crisp outline were the true body, the dimming should match it. But if the outline is a constructed scattering wall, the dimming shifts with the wall. Now think about what that implies. 3i Atlas can create a false coma that isn't just dust because comets do dust. It's dust in the right density, right distance, right timing to act like a mask. And the mask has two jobs. Job 1. Keep the visible diameter in the boring range where headlines stop caring and models assume a normal small comet. Job 2. Scramble any attempt to reconstruct true geometry by making the boundary you measure belong to the sheath, not the body. NASA doesn't need to believe in intent to be forced into that conclusion. They just need to accept the behavior is state-driven and repeatable. So they started describing 3i Atlas as having two layers in practice. A physical core that thermal data insists is not trivial, and an optical boundary layer that can tighten or loosen to fake the apparent cross-section. That's still comet physics in the conservative framing, just an unusually efficient version, but it's also exactly how you design a camouflage system if you wanted to be misclassified by quick-look surveys. Then the cycle showed up again, because it always shows up. The sheath thickened at a predictable phase, the visible limb sharpened, the size estimate shrank, and the public-facing normal comet narrative stayed intact. Then the sheath relaxed, the infrared baseline stayed steady, and the mismatch returned like a bruise you can't cover. NASA's analysts began marking sessions with a state label, like weather. State A, bright limb, small apparent nucleus, stronger fine-grained polarization. State B, softer limb, larger apparent coma, different scattering slope, and the transitions between A and B were too fast for slow rotation to be the main driver. Rotation can modulate, sure, but these were switches, not waves. Which leaves one hard question, the one that forces the next escalation. If the sheath is doing the masking, what triggers the sheath to thicken and thin on command? Solar input alone doesn't fit because the rhythm keeps going when solar conditions are steady. So the team began to suspect internal control through vent gating, charge effects, or something like a cyclic release and refreeze process. A physical clock that can pulse out micrograins, then clamp down, then pulse again. And that brings you to the next move NASA didn't want to take, but had to. If reflected light is compromised, and thermal gives only area, then you need a constraint that cares about shape in a different way. You need dynamics. You need to see how the object's motion responds when it shifts states, because mass and outflow leave fingerprints and trajectory residuals. You know what JPL trusts when light starts playing games? Motion. Because you can dim yourself, you can sparkle, you can blur, but your trajectory keeps receipts. They pulled the orbit residuals, the tiny differences between where 3i Atlas should be and where 3i Atlas actually is, and they lined those differences up with the mass states. Not weeks apart, same day, same cycle, same observation blocks. If the sheath thickens and thins, it has to move mass, and moving mass can push back. At first, the residuals look like noise, the kind you blame on a bad star catalog, or a small modeling mismatch you can smooth away with enough averaging. Then they stopped averaging. They sliced the data by state. State A, the tight sheath and sharp limb, versus state B, the relaxed sheath and softer edge. That's when a pattern showed up that was too clean to ignore. Each time 3i Atlas snapped into state A, the residuals shifted in the same direction. Small, ridiculously small, but repeatable, like a fingertip tap on a table you're trying to keep perfectly still. The shift wasn't constant thrust like a rocket. It looked like an impulse, a brief kick, then a drift back as the system returned to baseline. JPL did the obvious check. Could solar radiation pressure do it? Could a change in apparent area change the push from sunlight enough to fake a kick? It couldn't. The direction and timing didn't fit pure sunlight pressure, and the magnitude implied something closer to mass flow than light pressure. So they looked at outgassing, the Comet classic. Gas jets can act like tiny engines if they're asymmetric, and a sheath event could be jet control. ALMA had already shown the near-field grain density rising during state A. Now the orbit data suggested that rise is not passive, it's tied to momentum. In plain terms, when the mass tightens, something is leaving the body in a structured way, and the body reacts like it just fired a microthruster. But here's the twist. The kick direction wasn't random like messy vents. It clustered around a consistent vector in the object's frame. That's the fourth fingerprint. Random vents give you scatter. A consistent vector means a preferred channel, a stable nozzle, or a field-shaped exhaust. NASA didn't write nozzle. They wrote directional, non-gravitational acceleration correlated with brightness state transitions. Translation, the push happens when the mass changes, and it pushes the same way more often than chance should allow. Now you're probably thinking, so it's just a comet with jets, and that would be comforting if the rest of the behavior looked like normal jets. Normal jets flare with sunlight and rotate with the body. 3i Atlas's kicks lined up with cadence boundaries and the 47-minute beat. That's not impossible in nature, but it is rare, because it implies the venting is gated by an internal clock, not just by heat on the surface. JPL ran a simple energy budget. To create the observed impulse, you need a certain mass flow at a certain speed for a short window. The numbers weren't insane, but the control was. A short clean burst, then a stop, then another burst on the next cycle like it's scheduled. And the burst timing matched the moment the sheath thickened, as if the object first builds a scattering wall, then vents through it. Imagine a valve that first closes the leaks, then opens one outlet hard, then closes again. The leaks make you bright and messy, one outlet makes you stable. If you can do that, you can keep your optical story boring while still bleeding energy in a direction your orbit will remember. NASA tried to break the pattern by watching during a quieter cadence, fewer telescopes, less attention, hoping the mask would relax and the kicks would vanish. The mask still cycled, the kicks still appeared, weaker but present, like the system doesn't care how many eyes are on it, only where it is in its beat. That killed the "it reacts to us" idea and replaced it with something worse. It's running its own routine, and we're just catching frames of it. Then JPL compared the kick moments to the DSN boundary lead they had mapped before, the screen forming ahead of the heat. The kick didn't follow the heat peak, it followed the boundary formation, as if the envelope locks, then the impulse fires, then the surface warms after. Boundary first, impulse second, heat third, chemistry last. That chain kept repeating like a program you can't interrupt. And now you see why the mask matters. It's not just hiding size, it's part of the mechanism that lets the object manage how it interacts with space. The most honest internal question became, is the sheath a byproduct of venting, or is it a control layer that makes venting behave like thrust? Because if it's a control layer, then the false size isn't cosmetic. It's functional, a system that shapes scattering and momentum together. NASA kept the public language calm. No impact risk, trajectory stable. All true. But internally, the phrase that kept coming back was engine-like. Not because they saw flames, but because they saw repeatable impulse and repeatable state control. The two ingredients that make motion feel deliberate. And that leads straight to the next move. If you suspect a controlled impulse, you don't just watch brightness. You hunt for the exhaust signature itself. You know what NASA does when it suspects a kick without an engine? They stop debating the word and start hunting the exhaust, because exhaust is physics you can point at. JPL gave ALMA and Webb one job: catch the impulse window, not the pretty peak. They wanted the minutes where the orbit residuals jump. That meant timing the observation not for maximum brightness, but for the boundary formation phase, the moment the screen snaps into state A. ALMA watched for cold gas lines that shouldn't spike cleanly if this is just messy sunlight-driven venting. Webb watched for a subtle thermal change that could mark a vent opening even if the overall surface temperature doesn't swing much. Ground teams watch polarization like a heartbeat, because if the sheath is built from micrograins, the scattering signature should shift first. The first cycle hit, and at the boundary snap, polarization jumped exactly as before, like the mask pulled tight. Then ALMA caught a brief emission feature that looked like a narrow plume, compact and directional, not a broad coma swelling in every direction. It wasn't a giant tail, and that's what made it scary. Big natural comets get messy. This looked like a controlled leak. The plume appeared, held for a short window, then thinned fast, like a valve closing. Webb saw a tiny, localized thermal bloom near a fracture line, not the usual seam area, and the bloom faded as the plume faded. Then the orbit residuals logged the impulse right on schedule, in the same direction cluster JPL had been seeing. That alignment was too clean to shrug off. Mass tightens, plume appears, microbloom, orbital kick, plume vanishes, and the object goes back to normal. NASA tried to blame it on a one-off event, because everyone wants a one-off, but the next cycle repeated the same choreography. Not identical in strength, but identical in order, like a routine with variable intensity but fixed sequence. ALMA's plume axis matched the preferred kick vector within the uncertainties, which is the closest you get to a smoking gun in deep space. If a plume pushes you, its direction matters. Here the direction wasn't drifting randomly with tumbling, it stayed anchored. That suggests one of two things. Either the body's rotation is locked in a stable orientation relative to the flow, which is rare for a loose comet, or the exhaust is being guided by a field structure that doesn't care about the surface shape the way tumbling does. Remember the tilted sheet boundary DSN reconstructed, the screen that forms ahead of heat. If that sheet can guide charged particles and micrograins, it can act like a nozzle without metal, shaping where the outflow goes. A comet can vent through a crack, sure, but a crack doesn't normally create the same directional plume over and over on a clock. A field-guided outlet can, and the field-guided idea got stronger when Webb looked at the spectrum during the plume window. The signature wasn't just warm dust, it hinted at a colder component mixed in, like grains or molecules that shouldn't be this organized in a chaotic vent. Cold, narrow, fast, and clean is not how you describe typical comet outbursts. It's how you describe controlled release from a reservoir that's been sealed until a trigger. Now the mass makes more sense. A tight sheath of grains can serve as the boundary layer that keeps the environment stable until release. It can also shape the optical edge, making the nucleus look small and boring while the real mechanics happen inside the sheath. So NASA began framing the disguise as part of a coupled system. Optical mask to control classification, sheath to control the boundary to control exhaust geometry, exhaust to produce the kick. That chain is still physics, but it's physics behaving like a design. Then they ran the final sanity test. If the plume is real and directional, it should leave a faint signature in the dust distribution afterward. Not a tail you see with your eyes, but a slight asymmetry in the near field dust, a lingering skew that matches the plume direction. Ground telescopes caught a subtle asymmetry after each impulse, small but consistent, like the system leaves a footprint in its own dust. And the footprint faded, because the sheath reforms and re-randomizes the grains, erasing the evidence like it's wiping a board. The team's internal language tightened again. They stopped calling it coma variability. They started calling it state-controlled outflow. Controlled doesn't mean intelligent, but it does mean, constrained by something that behaves like a regulator. And now you're ready for the next question that changes the whole story. If 3i Atlas can build a mass to look small, and it can vent in a way that produces repeatable impulses, then its reported size isn't just wrong. It's strategically wrong in exactly the direction that keeps everyone calm. Because a normal comet has normal mass assumptions, normal risk assumptions, normal observation priorities. A bigger, flatter, field-coupled body would get a different level of attention, and 3i Atlas kept dodging that label. You know what's funny about confirmed size claims? They usually mean one model, one wavelength, one assumption, and 1,000 quiet compromises. So NASA tried to remove the excuses. Same night, overlapping windows, visible light, near IR, thermal, millimeter hints, plus polarization as the lie detector. The goal was simple: solve for one consistent body that explains everything at once, instead of letting each instrument invent its own reasonable size. They built an inversion like a courtroom reconstruction. If the nucleus is X, the albedo must be Y, and the temperature field must land in zeta. If the coma adds brightness, you can model that too, but it should follow smooth laws, not sharp steps that magically appear on schedule. They picked a phase angle range where geometry barely shifts, because geometry is the favorite hiding place of bad interpretations. Then they set the trap, continuous multiband photometry while Webb tracks thermal area, with ALMA watching for the near-field sheath to thicken. In a normal comet, the curves dance together. Visible gets brighter as dust rises, thermal rises more slowly. Polarization changes in predictable arcs. 3i Atlas did the first half perfectly, which is how it always lures you into thinking you finally have it pinned. The inversion converged on a boring diameter. Not tiny, not huge, just plausible enough to let everyone breathe. Then mid-pass, without a geometry reason, the visible scattering law changed. Not it dimmed, the slope changed, the way brightness responded to angle and wavelength shifted like someone swapped the skin. Color index jumped toward darker, flatter reflection, while the thermal area refused to follow, staying stubborn like a body that didn't shrink. Polarization didn't drift smoothly into a new phase, it snapped into a different regime, the signature of finer grains, dominating the reflection. The inversion broke in the most revealing way. It produced a second solution that fit the new scattering law, but that solution implied a different diameter. 2 diameters from the same object in the same hour, with the only difference being how the light was being scattered back at us. NASA reran the fit with stricter priors, forcing the diameter to stay fixed and letting albedo float wildly, hoping it was just reflectivity. The model demanded albedo swings that were physically ugly, too fast and too large, like frost forming and evaporating on a schedule. They let coma parameters absorb the change instead, but the coma needed to become a tight, sharp boundary layer, not a diffuse cloud. And the moment they admitted boundary layer, ALMA's data clicked into place like a key. Right when the scattering law flipped, the compact near-field grain density thickened. Not a tail, a sheath, close enough to act like an optical surface. So the nucleus edge the camera loved wasn't the edge of rock or ice at all. It was the edge of the sheath pretending to be the body. That's why the diameter fork happens. You're not measuring a fixed object, you're measuring a moving optical boundary that can expand or contract. Webb's thermal area stayed steady because the real emitter didn't change. The sheath just changed, which photons it allowed to escape cleanly. JPL tried a harsh sanity check. Treat the visible limb as fake and trust only thermal plus dynamics, then see if the kick moments align. They did. The impulse clustered after sheath tightening, not after heat peak, like the object pays a propulsion price to maintain the disguise. So NASA's internal language shifted again, from uncertain diameter to something more clinical and more alarming. Apparent cross-section is not a stable property of this target. That's a polite way to say you cannot trust a single headline size, because the object can present multiple sizes depending on state. And the states aren't slow seasonal changes, they're fast, clocked, and repeatable, the kind of behavior that turns measurement error into system. Now you're probably wondering why this matters if it's not on a collision path. Because size drives everything: mass guesses, outgassing thrust estimates, how strongly it can sculpt its environment, and how you predict future anomalies. If the object can keep itself categorized as ordinary, it buys time. It reduces scrutiny, and it turns every quick survey into a false comfort. And the inversion test proves something brutal. The mask isn't a metaphor. It's measurable, state-dependent, and it can fork reality into 2 answers. You know what NASA does when a target starts responding to observation cadence? They stop giving it a rhythm to respond to. They called it the blind schedule. No public calendar, no predictable blocks, no tidy handoffs between Hubble, Webb, and the ground arrays. The idea was simple. If the mass flips because of our cadence, then randomness should break the correlation and expose the real behavior. So they generated observation windows like dice throws. Then only the operators knew the times, and even they got them late. Hubble would open in one filter, then switch without warning. Webb would sample thermal in short bursts, with long, quiet gaps. ALMA would take quick snaps of the irregular spacing, hunting for the compact sheath without giving it a steady beat to lean on. DSN logged radio path noise continuously, because if the boundary layer is real, it leaves fingerprints in phase and timing. For one full night, the data looked almost normal. No sharp forks in diameter, no dramatic scattering swaps, no 2 sizes. Then at the worst possible moment, the mask flipped anyway, right in the middle of an unannounced window that shouldn't exist to it. Visible brightness dropped in a step, color flattened, polarization jumped, and the limb sharpened like a clean cut. Webb's thermal area stayed steady, which meant the body didn't shrink, but the visible size collapsed exactly as before. Alma caught the sheath thickening in the same minutes, like a curtain being pulled tight around the nucleus. JPL stared at the timeline and felt the floor move. The flip aligned with nothing on the human schedule, but it aligned with the internal beat. The 47-minute cycle hit its phase marker, and the system changed state like it was obeying a clock we didn't invent. That's when the blind schedule stopped being a test of reaction to us, and became a test of what runs inside it. Because if it flips without our cues, then the mask is not a response, it's a routine, and we are just catching it mid-loop. NASA tried to force a different conclusion. They searched for a solar wind spike, a magnetized stream, anything external to blame. Space weather was quiet enough to make that excuse weak. No shock front, no sudden pressure wall, no obvious trigger. So they asked a harder question: if the mask is a routine, what is it optimizing for, and why does it keep choosing small? The answer in the room was never spoken as a single sentence. It emerged as a pattern of priorities in the data. When the sheath tightens, the apparent cross-section shrinks, but the plume becomes cleaner and more directional. When the sheath relaxes, the object looks bigger and fuzzier, but the impulse becomes less coherent, more like normal comet spill. That trade-off feels like control. Tight state for stability, loose state for venting, like breathing through a valve instead of a cough. And the blind schedule night gave them a gift. A state flip happened during a background star drift they weren't even aiming for. A faint star dimmed in a skewed way, not centered on the visible limb, but offset along the sheath boundary line. It was the cleanest hint yet that the sharp limb is a manufactured edge, a scattering wall, not the physical body. Hubble's images showed a crisp outline, but the star dimming traced a larger, asymmetrical silhouette that thermal data had been implying all along. NASA didn't say mask in any public note, but internally the word cloak started appearing in messages that were supposed to be sterile. Not because anyone wanted drama, but because state-dependent optical boundary layer is a mouthful you can't whisper at 2 a.m. The next move was brutal. If the mask is routine, you don't fight it with cadence. You fight it with phase. You predict the next flip from the internal clock, then you catch the transition at maximum resolution from every instrument at once. JPL built a phase model from weeks of cycles, then scheduled a narrow strike window around the expected state boundary. This time they didn't care if 3i Atlas knew it was being watched, they wanted the moment the sheath forms, not the story after. When the clock hit, the sheath thickened first, then the plume opened, then the orbit residual kicked, then the thermal bloom followed. Same order, again, like a chain that only makes sense if the boundary is the control layer and the heat is downstream. And right at the flip, the visible reflectivity didn't just drop, it changed scattering law as if the grain sizes in the sheath shifted. That's a level deeper than more dust. That's selecting the dust because different grain sizes scatter different colors and polarizations. Alma hinted that the molecular ratios also pivoted at the boundary, like the outlet is not always releasing the same inventory. So the mask is not one trick, it's a stack of tricks. Grain control, sheath geometry, and outflow gating, all phase locked. Now you can see why NASA's size statement becomes slippery. They can report an apparent diameter, but the object can reskin itself mid-measurement. And if it can do that, then every old survey frame becomes suspect. Not wrong, just incomplete, like photos of a person wearing different coats. The quiet nightmare is this: the true body could be larger, flatter, and more massive than the visible story suggests. Not enough to threaten Earth by impact, but enough to rewrite what comet physics can do when a body is big and state-controlled. You know what mass does to a mystery? It makes it heavier, not in poetry, in math. And math doesn't care what your photos look like. JPL took the impulse moments and treated them like a scale. If 3i Atlas kicks itself, the kick has a momentum cost you can estimate. Momentum is simple enough to feel in your bones. If a small thing spits gas, it jerks a lot. If a heavy thing spits gas, it barely flinches. 3. Atlas barely flinched. The residuals were real, but small, and that's where the mass starts to look less like style and more like strategy. They assumed a range of exhaust speeds because you don't know if it's warm vapor or cold jets carrying grains at high velocity. Then they computed the mass needed to keep the observed kick in the gentle tap range instead of a visible wobble. The first result came back too big for comfort. Not planet big, but big enough that the label ordinary comet nucleus stopped fitting cleanly. So they tried to save it. They lowered the exhaust speed, raised the uncertainty, widened every error bar they could widen without lying. The mass estimate still wouldn't collapse into the tiny range that matches the normal comet brightness story. Because if 3i Atlas were as small as the visible diameter implies, the same impulse budget would shove its orbit harder than what DSN and astrometry allow. It's the same logic as pushing a shopping cart versus a truck. The cart moves. The truck shrugs. 3. I-Atlas kept shrugging. That forced the next step. Compare it to known comets with known non-gravitational effects, the classic A1 and A2 style parameters. Normal comets show acceleration changes that are noisy, seasonal, and tied to solar heating as they rotate and warm. 3. I-Atlas showed a cleaner, phase-lock structure, like the same outlet keeps doing the same job on the same schedule. So JPL asked the ugly question. If the outlet is consistent and the kick is modest, what does that imply about the inertia behind it? Bigger inertia means more mass. More mass means either a larger body, a denser body, or a body carrying hidden material close to it. And that hidden material idea snapped back to the sheath. If the sheath is thick enough to shape optics, it might also be thick enough to carry momentum, like a surrounding layer of grains moving with the core. Not a giant cloud trailing behind, but a bound, near-field environment that behaves like part of the system. Alma's compact dust hints started to matter more. If the near-field grains are repeatedly rebuilt, then the system has a reservoir and a gate. A reservoir and a gate are what you need to run the same action repeatedly without turning into a chaotic, flaring mess. Now here's the simple way to feel it. If the mass can make 3 I-Atlas look smaller, it also makes you assume less mass, which makes any engine-like effect look more dramatic than it is. But the orbit says the opposite. The effect is subtle, which implies the mass is larger than the apparent size story wants you to believe. So NASA's internal brief stopped focusing on diameter and started focusing on inertia class. They never wrote that as a headline, but the way they grouped it changed, the way they assigned follow-ups changed, the way they prioritized instruments changed. Webb was told to keep thermal area as the anchor. Hubble was told to treat visible limb as a state artifact, not a body edge. DSN was told to watch the residuals around predicted phase flips, because that's where the mass inference gets sharp. Then a new contradiction appeared, the kind that makes a room go quiet. If the body is heavier, it should be harder for sunlight to drive such clean sheath rebuilds at this distance. Yet the sheath rebuilds kept happening on the beat, like it had its own energy budget, not borrowed from weak solar warmth. So they looked for internal storage, not a fantasy power source, but mundane things that still change the game. Trapped volatiles under a sealing crust, pressure pockets that vent only when a gate opens, phase change cycling that releases grains like clockwork. All possible, all physical, and still unsettling, because they make the routine feel less like weather and more like machinery. JPL ran one more test. If the mass is higher and the kicks are real, then the cumulative drift over months should be detectable as a slow bias. They found it, faint but consistent, like a long sentence written in tiny letters across the orbit. Not enough to threaten Earth, not enough to scream propulsion, but enough to prove the impulses add up. And the direction of that long bias matched the same preferred vector, the same outlet geometry, the same story the plume hinted at. So the mass estimate tightened again, because a consistent long bias is harder to handwave than isolated noisy points. Now you're at the point where false size becomes more than an optics problem. If 3 I-Atlas is heavier than it looks, then its interaction with fields, plasma, and dust is not the interaction of a small, weak snowball. It's the interaction of a larger system wearing a smaller label. And that's why NASA's public wording stayed calm while the internal tone got sharper. They didn't need to say masking out loud to act like they believed in it, because their scheduling, modeling, and instrument choices already did. The final line in the brief wasn't dramatic, it was practical. If inertia is elevated, apparent size is not a safe proxy for risk classification or for modeling non-gravitational forces. Translation, stop trusting the costume.